Let's look at this data path and try to figure out what are the control signals coming out of the controller to control the data flow through this different component of this whole logic circuit in the processor uh, data path part of the processor. So we can see there are a list of bunch of control signal here. For example, if I just zoom in, for example, like we see all these multiplexers has a selection signals. They are part of the control signals, and also register loads like the program counter load or instruction register load. Those are as well. Those are also control signals, and these are the register R and register W, etc. We have Alu operations, and we have like address selection, for example, MA select 2, etc. So these are the signals coming out of the controller per instruction, and they can be differ a little bit from each other. So if we want to formalize that whole control signal generation and how we want to actually create something called a micro instruction, which is nothing but composed of these individual control signals, and if we just convert into a machine code, that becomes a controller code, micro code they call it, for the microprocessor. So here let's list them down, and let's assume that we have a control signal bus which is like 29 bit for our case, 0 to 28, 0 to 28, right? Control 0 to control 28, and each of this bit of this bus is connected to one of the control signal that is being depicted into this data path. You all have access to this I think it's a JPG, maybe GIF, but whatever it is, like you can, this is an image, you can load in the image viewer and just zoom in and to see the names and everything into the of the diagram. So these control signals are connected to each of these individual control signals in the data path, and they are the maps, right? This is like, for example, ALU operation 5 fifth bit is connected to the control signal generated from the controller, that bus, the 19th 20th bit, basically it's on 90, index 19. So they are, this is the control bus, this is the control word. If we just convert these bits into the hex value, it becomes a control word or micro instruction, we call it. And each micro instruction from the controller is sent to the data path on this each phase, right? We have this instruction fetch phase, right, and instruction decode, instruction execute, memory. These are all these state cycles that is being five state cycle of the processor. um, and okay, this column is talking about, okay, if we just list down all the bits and then we start grouping them into 4 bits from the LSB side, then we are trying to will be ending up in a hex equivalent of that bit pattern. But anyway, that will come later. What else? Let me just try to classify this list of signals. Some of the signals are related to some certain common operation. For example, uh, anything like PC underscore, they are related to the program counter. Okay, so maybe we should just mark it as a group. For example, maybe we'll just highlight them as these, right? And then so if we just take a look like what I mean by the group, So if you look at this part of this data path, let me just zoom in a little bit. So if you look at the source, this is the input part of the program counter, right? And the source, if we can trace back from here, so this line, so this multiplexer is one of the data source of that, and which is being selected from this line and that line. So PC select 3 is one of the control signal that's controlling the value of program counter, right? So this input back to here, and then if we trace back this path, then there is nothing control, it's just an 6-bit 0 extender. uh, but the other path is another multiplexer here, so PC select 2 is also controlling the value of the program counter, right, in the next cycle. And if we trace back this path, then PC select 1 will be also controlling the data of the PC. And then there is nothing controlled. Here is the adder, here is the adder, they're not a control. So they are basically related to the value of the next value of the PC. That's what I'm just trying to group them so that we can treat them as a whole in a specific cycle or specific state of the processor execution. Um, so we group them, and then let's say this is more like independent instruction IR load. So if we go back to the data path, this is my IR load, instruction load register. At this point, just note that this instruction register, we are using a latch instead of a flip-flop, just to avoid the complexity that if it is a flip-flop, it need to wait for another clock cycle for the data to be loaded, whereas if it is a latch, then the instruction will be loaded in the same clock cycle as the data coming in. So that gives us a little bit consideration, a little bit easiness, I would say, for this cycle synchronization. So at basic, like let's think this is a latch, not a flop. Unlike this one is a like a register, really they're using a flip-flop circuit there, but it is a latch based register just to avoid some complexity of extending cycle and stuff like that. If you need to understand more on this part, please contact me, okay, or come to my office hour, then we can discuss more about this, why we are just assuming this is a latch versus this one is a flip-flop, okay. But let's assume this is a latch, and we have a control to load that latch IR load, which is kind of pretty much independent from a grouping perspective. And then I would say these three, we can possibly group them together. Let's just use some other color there, maybe like this color. Okay, so this is all related to my register operation, register controls. Okay, and R1 select, let's see what is that. R1 select is I think this one, right? So it is used for the push and pop operation, but it is practically selecting the address of the R1 register to be read from this register file. So this is kind of accessing the register, especially during the read or register fetch stage. So we are grouping them, grouping it with this register R and register W, and we can also group this is read, okay, and another related grouping would be these two with this WA selection. Okay, these are the right address selection. It has bunch of control signals are involved there to determine the right address of the register during the write back. So let's also group them WA selection. Let's put it salmon. Okay, the same color as this one. These are all related to that register, address selection, read and write. Okay, and what other groups? SP load is pretty much standalone. This is a stack pointer load control signal, which is right. Okay, let's just. Oh, here is a stack pointer, right? This is a stack pointer register. So SP load is pretty much standalone. It's not kind of related to any grouping or anything like that. Then we can group the other is as a operand selects, right? It is all related to the ALU operation, and if you see, trace back the two inputs, right? It is like OP1 select 1, and then it's pretty much there. We don't have anything like OP1 selection 2, because we just need to distinguish the R1 register, sorry, the operand 1 of the ALU between two different data source. But for the operand 2, we have quite a bit, like OP2 select 1, 2, 3, 4. Okay, so let's group them like OP1 and OP2. These are all related to my ALU operation operand selection, right? So OP1, these, let's just group them. Let's put a different color there. An ALU operation code, that 6-bit code, it's pretty much they are grouped by itself. So let me put another color there, another groups, and we have two more. One is the memory address selection. Memory data selection is standalone by itself, and write data selection. Okay, so memory address selection 1 and 2, what are they? They are okay, right here, these two multiplexer. Okay, it is the address that is going out to the memory device. It can be either from my PC, okay, which is kind of used for the register, for the address to read from a instruction address. Okay, so let's put it that way. So because your program counter is pointing to your instruction part of the memory, so whenever we are trying to read from that area, we remember our memory is hosting both the program and the data, and they are of course in a different addresses. So whenever we are trying to go and access instruction part of the memory, that data is coming directly from my program counter, right? This way. So MS select 2 and MS select 1, the other path is either selecting from either between the stack pointer or a memory address which is being computed by the ALU, the address being computed by the ALU for load word and store word instruction. Okay, so if we are executing a load word or store word instruction, then this ALU is computing that address, and that address has to follow through and be sent out to the memory device and address, right? And if we are doing like a push and pop kind of operation, then stack pointer register is actually source of that address for the memory. Okay, so that too becomes a group for me. So let's make them a group. Okay, okay, let's put like that. And MD memory data selection 1, that is just one signal. We can just see what is that. Oh, here it is, right? So it is either I am writing out from the register 1 into the memory, or register 2 from the memory, seems like, right? So this multiplexer is selecting between data which is coming from R1 data, this output, okay, and R2 data. It is selecting between them and to send out as a data out, because all we know, like we are when during the program execution, we are not we won't be writing to the text part or the code part of the memory. We'll be only writing the data part of the memory, and those data sources are practically our register file. Either one of them, R1 or R2, we will be selecting from them. Okay. And the last group, but definitely not the least, is my right destination selection. Okay, so or right data selection, I would say, not destination, right data selection. So my data right has couple of sources, right? So either it can be coming from the memory, directly from the memory. So this is a data in for the processor, which is kind of connected to my data out port of the memory. So it is from the memory. Some data is being driven for write back, like kind of a load word instruction, like which reads from the memory. Memory sends the data in the data in line, and that data has to be written back into my register file, which will be involved with WD selection 2 and WD selection 3. Just if you just follow through this multiplexer chain, right? And there is a WD selection 1 as well, which is like either I can have a data back from the memory or from the ALU operation. Like for example, add operation writes back to the register the result of the ALU operation, right? So one data source can be the ALU operation. So that's the WD selection 1 that controls it. And then I think this multiplexer controls it's a LUI, maybe load upper immediate, that data path to support it. And this one supports, I believe, let's trace it back, PC plus 1, that is, I think, right, this if we trace back this path of this multiplexer, which is tracing back into PC plus 1, right, PC plus 1. So this is the data path for the RA, for the JL instruction, right, to store the PC plus 1 into the register file, register 31, I think. Anyway, but 0, but just look at that. We need to look at that instruction set specification, which registered to be updated for a JL kind of instruction. Okay, so but anyway, those are the groups for the write data. So it will be like where is that? Here, write data. So let me just put another color there, maybe this. Okay, so we just explain the different groups of the signals, what we can consider together when we are trying to determine their value in a specific cycle of the processors, like instruction fetch or instruction decode execute, and those kind of thing. Now let's review the micro instruction generation from control unit for the instruction execution of add $S3 S2 S1, for example. Okay, just some registers. So for our case, it will be maybe S3 is not that much clear to you. It may be like what we call about like register 3, maybe register 2, register 1. Okay, just for from our notation perspective. Okay, S3 S1 is more like an MIPS processor registers. Since we are dealing with our own processor, let's just put some generic name there, R3, R2, R1. Okay, so during the instruction fetch, what happens is that PC is already pointing to the next instruction to be picked up from the memory, right? So this PC, this PC or program counter is having an address of the next instruction. So what essentially we want to do in this data path is to make sure this address going towards the memory is actually picking up an address from the program counter, right? So this is the path. This program counter is driving that address into the one terminal of the terminal 1 of the multiplexer. So that means my MA selection address 2 must be 1 at that point, whereas memory address selection, it really does not matter if it is 1 or 0, but means it's a don't care, right? But for our example of control signal generation, we need to come to a point, come to a definite Boolean value. We cannot just put a X there. Okay, so what we assume always, if it is a don't care, we put a 0. Okay, if it is a don't care. So MA selection 1 is really doesn't matter whether we put 1 or 0, because ultimately it won't be selected through this multiplexer, because we are setting the MA selection 2 as 1, so that we can push the program counter address to this path into the memory. So we are placing we are making the MA selection 2 as 1, and then this is a don't care, but for a don't care, let's put 0. Okay, always that's a thumb rule. So for this instruction fetch, what all we need to do is memory selection 2 as put as 1, this is a 0, and then we need to make sure we are reading from the memory. Okay, so 1 0. Okay, now let's assume at this point 0 0 is a hold for my memory and also for the register file. Okay, 0 0 configure, if we put both reg r0 and reg w0, it's a hold for the register file, means holding the previous read output at the output ports like r1 data and r2 data, and 1 1 is an invalid operation. Okay, so it's an let's say we don't use 1 1 at all, reg r and reg w. Similarly for the memory signals, right? So this data path is only including your control signal within the processor, but of course there is controller need to control also the memory operation. So we are actually listing down that memory signal separately, which is not becomes essentially part of the my control or micro instruction from the microcontroller. Let's just keep it at separate. Okay, so we are reading from that memory, and address been selected as a PC through this selection, and MA selection 1 was don't care, so we put a 0 there. So this phase we read the instruction. Okay, so are we care about anything else, because we are memory is in read, so it doesn't matter what data being read and etc etc. But there are a couple of things, like whenever there is a sequential element, like for this data path we have program counter, we have instruction register, we have stack pointer, and we have register file. Okay, so we make sure that we are not putting a state of writing for those sequential elements. Okay, so that means we need to keep PC load as 0. We don't want to write or overwrite the PC at this point. We don't want to override the IR load at this point, instruction register. We don't want to override the stack pointer at this point, so we keep it 0. And also we don't want to write anything, so we want to make register file and a non-write mode, which means and register write must be a 0. Okay, now we can put it as a read mode, which probably won't harm in any way, but since our register file has a hold mode, I would suggest make it that into the hold mode. So hold mode for this register file, let's assume it says 00, read reg r0 and reg w0. So with that in mind, so we put all the sequential elements, that is IR load at 0, PC load at 0, SP load at 0, and also register read write as 0, 0. Okay, so rest of them is just don't care at this point, right? So we basically let's put, okay, these are, I'm just bold facing them because these are the must signals here for this operation. Everything else is a don't care for me. Okay, so we'll fill up the don't care with 0 later. Okay, let's just keep it like that. Okay, now next phase, so this is phase 1, instruction fetch. The instruction has been fetched now into the processor, and then instruction decode is where we want to load the instruction read from the memory in the previous cycle into my register, into my instruction register, right? So right here, so IR load must be 1 at this point. Okay, and we don't want to override the PC, we don't want to override the registers, we don't want to override the stack pointer, and at this point, since I have already read from the previous I've already read from the instruction memory, I can make this in hold configuration, this memory, and memory select in this case is don't care, so it is not important, right? So we just leave it aside. What else is important right now? Okay, we take care of the memory, we took care of the stack pointer not loading, instruction register has to be loaded. And by the way, at this point, this is not only instruction decode but register fetch as well, right? So instruction has been loaded into the instruction register, and then at the same cycle we need to make sure we are actually doing the register read correctly, right? So here in this case I need to read in RS and RT, right, as an R1 or 2. RT is being straight connected from the instruction bus, that instruction signal, but for the R1 I need to make sure it is coming from the RS field, not as a 0. So this guy R1 select 1 must be into 0. So R1 select 1 must be 0. And wait a minute, we need to read the register, so I must put a 1 here, right? 1 0, that's the register read. We make sure RS is correct, we are loading the instruction on the instruction register, we are not overriding stack pointer, and we are also not doing any write, or we are just keeping the hold on the memory at this point, right? So these are, okay, let me boldface, these are the required signal. Okay, now so we're done with the register fetch here. So for next instruction we must keep this as 0, we don't want to override. We also don't want to override the current instruction in the instruction register. At this point this guy doesn't matter, we just want to keep the register as on hold. Okay, and SP load as hold, that's important, and also memory controls as a hold. Okay, and now at this point what is happening, we need to make sure the ALU is getting the correct set of inputs, right, which is right from, need to be from R1 and R2, these two selection. Okay, So for this, you can pretty well see that most important control signal here to make sure R1 data is going out and be input into the ALU is that OP selection 1 must be at 0, right? So that's important. So let's make that OP selection 1 as 0. That's important. And then how about the second operation, right? R2. This guy needs to be in the ALU operand. So OP selection 4 must select 1, must be set to 1 so that we can pass this R2 data into my ALU operation. So OP2 selection 4 must be 1. OP selection 4 must be 1. Okay, so let me just boldface this one, this one is needed, right? And that will actually will select the right operand for the ALU, and ALU will produce result. Okay, now in the memory phase, I don't want to there is nothing memory related access here, so we are not reading or writing from the data memory for this instruction add. So this guy has to be 0, IR load has to be 0 and not changing it, SP load has to be 0. Let's hold the data from the register, and this doesn't matter right now because we're not doing any read or anything like that. So this is important, this is important, this is important, right? And then another thing is important, which is that since this is a combinational circuit, till my ALU operation result is being written back into the register, that means the result is committed. Before that, we must keep this current configuration on. Okay, so that means it this selection of this multiplexer and this multiplexer has to hold on till we write back the result. Okay, so we carry forward this control here and this control here. Okay, and then of course memory wise I'll just have 2 zeros. Okay, just hold. Now oh, wait a minute, in the exe phase we forgot about to talk about this guy, right? ALU operation, we need, that's also important. So ALU operation code, let's say we have remember we had one of the table in the slide. I think it's lecture 11. Okay, the ALU design that has an operation code for the ALUs, right? So let's assume that code is like this. I'm not sure what the code is. Oh, why don't we just open that file and just take a look. Okay, so this is the slide I was talking of, like the addition operation, the ALU operation code, right? So for add, we are doing the add example. So my operation code is 01, which has to be 01, right? So that means 1, which is 1 here, 0, 0, 0, 0, 0, right? So this is my add operation. Now this operation has to also, since this is a combinational circuit, okay, this operation code also has to be like carried over to the through the mem, okay, and also through the write back. Okay, so let me come back to the write back again. So we are done with the memory, I believe. Okay, Now, in the write back, we are writing back the result out of this two addition R2 R1, which is done at the exe phase, and we are carrying forward that through the memory. Now we need to keep that as well. So my operand selection has to carry it forward, and my operand 2 selection and also operation code of the ALU has to carry it forward. Okay, in the write back phase. And then I want to write. Okay, so register control, right? It has to be in a write mode. So 0 1, that is my write mode. Okay, SP load has to be 0, we don't want to disturb that. Okay, and IL load is also has to be 0, we don't want to disturb the instruction register as well. And this is don't care, etc, etc. And write address selection, I think that's important, because I want to what address, right? So I want to write into the RD, right? It is by definition that instruction is RD equals RS plus RT. So to make sure RD goes through and make it its way into the right address here, so we need to make sure your WS selection 1 is 0 and WS selection 3 is 1, where WS selection 2 is don't care, right? So WS selection 1 is 0, WS selection 1, which is here, must be 0, and WS selection 3 must be 1, right? So that's important, and then WS selection 2 is not important, which is don't care for me. And however, the write data has to be coming from the ALU, right? As an ALU is doing that addition, so WD selection 1 must be 0. WD selection 1 must be 0. So let's take that. Okay, and okay, which is also important for me. And then so it went through from ALU through this multiplexer, and I want to make sure that now this is my ALU data, and through this here I must select WD selections as a 0 because I want to make sure this data line is selected. So WD selection 2 is 0, and then this data is passing through this multiplexer, which is I must select to 1. So WD select 3 must be 1. WD select 3 must be 1. Okay, so here it goes. What else? W, this is don't care. Okay, D. Okay, if we take care of the right address selection, we take care of the right data selection. Nothing to do with memory selection. It's for the memory writing. I think that's to make sure everything is okay in place to write back my result into the register file. And also during this stage, your program counter must be updated to point to the next instruction, right? So our next instruction for this guy is always the very next instruction is PC plus 1. So what we all need to do, need to write back into the PC, that is I make it 1, and make sure PC plus 1 goes into the input of the program counter, right? So this guy must be PC plus 1. So to make that happen, PC select 1 must be 1, and PC select 2 must be 0, and PC select 3 must be 1, right? So PC select 1 must be 1, this must be 0, this must be 1. That's what we just determined from this data path, right? So PC plus 1 to go make through this multiplexer as PC select 1 has to be 1, then that has to go through this multiplexer, which we need to make it 0. PC select 2 as a 0, so that PC plus 1 makes through this multiplexer, and then we must make PC select 3 to make sure it is through this multiplexer to be back as so that the next PC can be set as a PC plus 1. So this should be our configuration. So write back phase is really kind of lot of important signal settings are there, seems like, whereas instruction fetch has only few are important. Okay, so once we have determined this guy, this important signal, everything else is a don't care for me, and don't care we replace by 0. Okay, so 0 0 0 0 0 0 0 0. Okay, so and then let's just have, okay, why don't I just put 0, everything is 0, 0, 0, what is that? Oh, okay, selection. Okay, and now 0 0. Okay, so I'm replacing every don't care term with zeros. Okay, so once it is done, then all we need to do, just change it to a hex code. So this is my control micro instruction code looks like, from control 0 bit that bit to control 28. Okay, now all we need to do is just group them into 4 and make an hex number 0 0 0 0 0. Then this guy is 2, this is 0, this is 0. So my control code really is, apart from this memory read and write, oh, we did not put anything here, so that would be 0, like we are just holding, we're not writing back anything in the memory, so this would be 0. So this guy microcontroller code would be 0x 0 0 2 1 2 3 4 5, right? 1 2 3 4 5. This is microcode. Okay, so this is the instruction fetch. During the instruction fetch, your controller should produce this microcode towards the data path. Okay, and we do similar like here 0, and this is like 1 2 4 8. Okay, 5 0 0 0 0 0 0. So this is more like okay, 6050. Okay, so 0 cross 50. Okay, and now this guy is 0 0 0. This is like 6 0 0 0 0. So 0 0 0 0 6, all zeros. Okay, 3 0 6 right. I think we are looking for like 8 hex digit, 2 4 6 7. What happened there? 0 1 2 3 4. Oh, here. Okay, 4 0 1 2 3 4, then 6, then another 3 zeros. Okay, okay, so this is the microcode at this point, exe phase. Okay, and then in the memory phase, what do we have? 0 0 0 6. I think we just repeat that code, right? I think this is a repetition of this code. And then I have some interesting here, which is like 8 10 11, right, which is B 8 0 6 0 0 2 1. Okay, so like 1 2 0 0 6 0 8B 0 8B. So this is my microcontroller code at the right backstage for the add instruction. So what happened, that each phase to execute this instruction add R3 R2 R1, our microcontroller controller part of this processor will start issuing this microcode to the data path, which is like connected like this, as we discussed in that signal mapping. So these are the microcode that will be issued, which is like a bit pattern wise. It is a 29-bit number, and that all these control signals are being issued like this. Okay, this is how we generate and control signal for any instruction. Okay, we'll go through two more example like BNE and POP really quick, just to make sure that we understand the differences between these two, different style of instructions. Maybe you want to do the store word, load word, that kind of make sure your memory phase has something to do with here as well on the memory read and write, right? So we'll review the BNE and POP. Okay, so let's save this. Okay, for the BNE operation, let me just quickly just copy over this color code into the BNE. And this one, instead of talking signal values at each phases, since we have some ideas about what phase is related to which signal, more or less, let's talk about a little bit in a different approach now. Okay, so you can definitely take this approach, like for BNE operation, what are the signals to be on the instruction phase, the decode, the exe and stuff like that. But BNE, let's see if we can do it like more efficiently as we understand more about how these signal assignments are done here. So for BNE, okay, so definitely we want to do a PC load here. So PC selection doesn't matter, right? PC load here. Oh no, sorry, wait a minute. No load. We don't want to load anything here. At this point, we don't want to disturb the instruction register. We don't want to disturb the stack pointer. So those are all like zeros. However, the register instruction fetch, we don't want to do anything. Just do a hold there, right? And then we want to do the memory instruction read. So that has to be definitely a read signal for the memories. Okay. Then on the PC load side, as we know that this guy will be loaded only at the right backstage, right? So this will be 1 always. Okay. Now for the BNE, okay, for this case it is like S3 is not S2 again. Okay, let me just change it for our convention. Okay, R3 instead of MIPS, R3 R2, and let's assume R3 is not equals R2. The content of R3 is not equals R2. So this thing, let's say, okay, this makes more sense. Okay, content of R3 and R2 are not same. So let's see. So what it will mean at the end of the day, it will pick up a branch address L1, right? Because we are assuming in the register file R3 content is not equal to R2 and we are executing a BNE. That means that at this point it will be jumping to the L1, right? And that data path jumping to the L1 path is my branch address, which is being generated by by your PC plus 1 plus this guy, right? This immediate address. Okay, this is the branch address in the instruction that is embedded in the instruction code, like the machine code of the instruction, and this adder is producing that branch address, right? Ultimately PC plus 1 plus this sign extended immediate, right? That is the branch address BNE data path for the program counter. So that means I must select PC select 2 to 1. PC select 1 is don't care, that means 0, and this guy PC select 3 must be also 1. So 2 and 3 must be 1, right? So 2 and 3 must be 1, and PC select 1 is don't care. Okay, so this becomes your pretty much of these group of signals configuration during the different stages. Okay, so let me just highlight them. Okay, why don't I just copy it from here, this header, Control C, okay, Control V. Okay, now how about the instruction load? Again, instruction load will be 1 at this point. Instruction fetch, after the instruction fetch, when the instruction decode is done, then it will be there, and everything else is 0. So Control C, V, and let's take care of the memory as well, right? Only at this point read write, read memory read should be there. Everything else should be hold, and we are not doing any other memory read or write at this point because they are not memory LW or SW kind of instruction. So 0 0, and let's add it here, and also here. Okay, so that took care of that control signal. However, the SP load, we are not at all doing anything related to the stack pointer, so we can apply, just put zeros there. We're not changing anything on the stack SP load point of view. And how about the register read write? We are reading from the register, okay, that ID and register fetch. Let's also encode the register fetch just to make sure we have no confusion. So at this phase we do both instruction decode and register fetch, right? So we must have a 1 and 0 here. 1 and 0 means that we are reading from the register. Okay, and that means since we are reading from the registers, which is like RS and RT, that means our R1 selection is also important at this point, which we want to make sure it is stayed at 0. Okay, so this is 0 is also important. Okay, register read. Now, am I writing back anything for this the instruction? Answer is no. So that means for rest of the phase, this register read write, I can put it pretty much to the hold mode. Okay, and what else we can say? R1 selection is important here, don't care about the other terms. However, the OP1 selection, okay, they are important because remember this BNE is implemented to the sub operation, right? It is an subtraction operation, right? The controller does a subtraction from the R1 and R2 between that, and then test this 0 out signal to make sure they are equal or not, because if they are equal, subtraction will result in 0, otherwise not. So it takes care. So ALU operation is basically your subtraction code in the exe, and we want to make sure OP select 1 is 0 and OP select 4 is 0. Sorry, 4 is 1 in this case, right? So OP select 1 for the exe phase is 0 and OP select 4 is 1. Important. And then we can just this select 1, 2 and 3 are kind of okay. Let's not worry about that right now. An operation code would be subtraction, which is 2, 0, 2. Okay, so that means it has to be 0, 1, 0, 0, 0, 0, right? That is a 2. So this is important. Okay, now, and this ultimately, right, we need to keep that result till again the W back stage, because we are using that result, that flag, to generate a control signal during the write back phase for the programming counter load to the branch address, right? So we must hold this ALU operation configuration till write back. So we are just keeping it. We are just keeping this guy. Okay, and then okay, how about okay? These are not important signals. Okay, write back. We talk about this thing. Okay, so we take care of this. Now MA1 selection, again this is important for the instruction phase, and which will be just similar to your add, right? So this is the same configuration. We are doing an instruction fetch, and then after that pretty much it is don't care. Memory data selection, which is not important right here because we're not doing a store word operation where it is important, okay, or push operation where it is important. So this is not important at all at any point of time. And how about the write date and write? This is all about register writing, and since this instruction is not about register writing back, it really doesn't matter, right? Remember, this register write is also there. We're not writing back. So this is the important control signals then for this instruction, and then we just put everything 0 to the other don't care places. Okay, so 0, 0. 0, 0 here, 0, 0, 0 here, 0, 0, 0 here. Okay, so we complete the control signal table, and as it is, we'll just make a hex micro instruction code out of this. This is 2, this is 0, 0. So 0, 0, 2, and 1, 0, 3, 4 zeros after that. 0 plus 0, 0, 2, 1, 2, 3, 4, 5, right? There are 5 zeros. 1, 2, 3, 4, 5. Okay. Yeah, so this is the same code as instruction fetch code. Microcode is same as a add operation, right? And then I have what here as 0, and then I have 5, 0, 0, 0, 0 0 0. So it is practically same as add. Yeah, 50, right? Yeah, I think so. 2 3 4 5 6 7 8. Okay, and here I have exe 0 0 0. This is 9 now. It is a little bit different. 9 and then 0 0 0 0, which is like 1 2 3 4. Okay, 0 cross 0 0 0 0, 9, and then I have 3 zeros. 1 2 3, 1 2 3 4 5 6 7 8. Okay, this is different than add, right? And then we make it through the next operation, same code. Memory is not involved, so if we just even do it manually, it would be same 0 0 0 9 0 0 0 0, and right back. That will be different from add because we don't have anything interesting, lot more interesting, like not that interesting like the add has lot of control signal to consider here since we are not writing back. Anyway, let's see what happens. Here is 8 plus 4 12 13, which is CD D 0 0. This is 9 0 0 0 0, which is like cross 1 2 3 4 9 0 D. Alright, so 1 2 3 4 5 6 7 8. Okay, so this becomes your microcode to be generated, or micro code to be generated from the controller to the data path at each phase: instruction fetch, decode, exe, mem, and wb. Okay, so this is how the BNE would work. And let's say like if we have this condition, let's say equals equals, right? Then what all you need to do is to take care of this selection signal to make sure that PC plus 1 goes through as a next program counter value. Okay, so it's a similar thing, but just consider that fact that we need to make the different value for the PC, next PC. Okay, now let's talk about the pop. Okay, pop, for pop you pretty much sure it is your next part, the pop signal. Okay, first of all let me just copy the color code here. Let me color code here. Okay, okay, and I just, let's say, have something like pop. Okay, so now for the pop, your PC load, program counter load, and selection pretty much works like your add, right? And similarly the IR load also is pretty much like an add. So I can actually copy it from that. So that's to make sure this guy is there. By the way, yeah, okay, yeah, we have the one here. So this is pretty much like this, like add or BNE at this point, right? But let's make sure we are copying from the add operation. Add operation. Okay, so this is pretty much it. And here I have this. Okay, now register selection. So pop reads from the memory pointed by the stack pointer and write back onto the register 31, right? Let's just make sure from our instruction set architecture. It's in the lecture 1, I believe. Yeah, here's a pop. Oh no, it's not register 31. It's a register 0 must be written back with the memory uh, pointed by the stack pointer. But before you access the memory, we must increase the stack pointer by 1, right? So first this operation happens, then this operation. Okay, let's keep that in our mind. So for us, we must have, do we have a register read at this point? No, it's pretty much stack pointer is a separate register, so we don't have anything to register read, right? So we can just put it as hold for the register file. We're not reading, so this R1 selection is not very important here, but we're writing back. Okay, so that must be 0 1, right? We are writing back into the register 0, which means while we are writing back register 0, during the write back phase, my WR address, write address must be 0, which is means WS selection 2 must be 0 and WS selection 3 must be 0. So let's fix that while we are here. What did I say? WS selection 2 and 3 both are 0, must be selection 2 and 3. Okay, WA I said, right? Okay, so here W2 and W3 must be 0. Okay, so they are must. So these guys don't care. How about data selection? So is coming back from the memory, okay, which is addressed by the stack pointer. But anyway, the data is from the memory, so we must have this data in WD selection as 1, WD selection as 1. Okay, and then that data must go through this guy WD selection to 0, and how about that one? Then WD selection as 1, right? This is 1, data memory data is selected. Then WD selection is 0, memory data is selected. WD selection is 3 is 1, that is selected. Okay, memory data, okay, 1. Okay, so this is a must, okay, for the write back into the registered 0. And what else? Okay, this selection is not important, we're not doing a register fetch here really. Okay, Nsp load. Okay, now sp load, of course in the register fetch it would be 0, this will be 0. sp load, I need to update it before the memory is accessed, right? So that means during the execution phase, let's keep it as 1. Okay, and then we don't want to disturb it during this phase. So this is 0, this is 0. So stack pointer would be updated before my memory is accessed, right? So stack pointer is updated first in the pop instruction and then the memory is accessed. So I'm doing that, okay, and then what it has to be, like we need to increase the stack pointer by 1, right? So let's look at that data path. So we will be using the ALU to have a stack pointer plus 1. So one of these guy operation would be and stack pointer. Okay, so OP selection 1 must be 1 at this phase. So OP selection 1 is 1, C Control V to so that I can select the stack pointer value, send it to the ALU. Okay, and I must select a 1 static. Somewhere I had a 1. Here it is, right? OP selection 2. That means I need to make OP selection 2 as 0 to make it the second operand as 1. OP selection 1, OP2 selection 1 as 0. Okay, and then that one need to be go to OP selection 2 selection 3 as 1. So OP selection 2 is not important, and so 1 is made through this path, and then need to make sure OP2 selection 4 is 0, so that one is go into the ALU. So stack pointer plus 1 is coming here, so by selection, so this guy has to be 0. OP selection 4 has to be 0 for my case, right? And OP selection 2 is don't care for me. Now and also we want to make sure this guy is in addition mode. On the exe phase, ALU is on the addition, which is code is 1, right? Just like add operation 0 0 0 0 0. This is must, and at that point we are also kind of updating the stack pointer with the stack pointer plus 1 at that phase. Now what happens? Question is, like, for add operation or even for the BNE, we actually made like carry forward that whole operand selection and the ALU operation code through the memory and the write back. Do we need to do that? Actually no, because this operation result is being consumed or at least written back or committed right at that exe phase cycle, right? So we don't need to carry forward this. So at this point this becomes like don't care. So it will become all 0, and eventually if you see, like, all zeros for the ALU is a no operation code, right? So just to make sure, see, no op 0. Okay, so that's even better. Like even for the add operation, look at this ALU operation code for other phase, it's a no op, right? Except for the where it matters. So for pop we don't need to carry forward, so everything is don't care, and we are not okay. Now memory address selection, let's talk about. So we took care of this whole thing, so we are done with practically this set. Now how about the memory address selection? Okay, so instruction fetch is same as the AND, so this will be like this. Okay, and it is important during the memory access again, okay, where I need to send the stack pointer address into as an address, right? That's where we are reading the data from, right? So stack pointer pop is all about stack pointer reading. So we are, whatever address this guy is storing, we want to send to the memory. So we must make sure MS selection 1 is 1, like stack pointer, this data coming through this multiplexer, MS selection 1 as 1, and then MS selection 2 as 0. That's a must be during your memory access phase, right? So this is 1, this is 0. So MS selection 1 during the mem, should be 1, and this guy should be 0. So this is a must here. Now once the data is read, so that means here it is read, instruction fetch, okay, and then it is a hold from the memory side, and then also it is hold during the execution. Now we are actually reading from the memory now, right, for the pop operation during the memory phase. So we want to make sure we are reading, and then in the write back we are holding the data, right? So we are holding the data. So our memory selection is important, and once the read is done, it is not important, so we don't care about that at this write back phase about the memory selection. Now, since we are not writing a data, this MD selection, memory data selection, is all about what data we are sending in, but that is only relevant if we are doing a store word or a push operation where we are writing into the memory. But here pop is reading from the memory, from the stack pointer address, so that's not matter. Now what matters, since we're writing back into the register file, WD and WA, those control signal matters at the write back phase, and which we already took care of, right? So these are the all necessary control signals so far we have derived for the pop. I believe we haven't actually skipped any important signal at an important phase. So what all we need to do is just replace the don't cares with zeros and make our hex code for our micro instruction or microcode. So this one, so exe phase for a pop instruction has more interesting signal sets which must have been set to some correct value, right? Most of the signals are important there. So here it goes 0. Okay, so we pretty much filled out a table, and then we can make the hex code. Here is 2 0 0. I believe its instruction fetch code is pretty much like standard so far. So, and then this guy become like 0 0 0 0 0 0. This is like 1 0. Okay, so all zeros one zero, right? Okay, and then how about this guy? This guy is 0 0 0 0. Now this is 5, this is 3, this is 0 0. So it is like 0 0 0 0 5 3 0 0. Okay, 0 cross 0 0 0 0 5 3 0 0. Right, and here then 0 0 1 0 0 0 0 oh, 0. So here my code is okay, 0 0 1 0. Okay, and now here it is, it's the same as the add, right? What does that be? Yeah, let's just cross check. 8 10 11 AB, yeah, B 8 0 0 0 8 1 0. So my microcode would at this point would be 0 1 8 0 0 0 0 1 8 0 0 0 8p. Okay, 1 2 3 4. Okay, so these are the control code, microcode of our micro instruction during the execution of our processor at different phases: instruction fetch, decode, execute, and your memory and write back phase. Okay,